Hey everyone, and welcome back for another deep dive. Today we'll be exploring the legacy of John von Neumann.
Oh, absolutely. A true giant in the world of mathematics.
And a pioneer in quantum mechanics.
Exactly.
We'll be drawing from an essay by Jurgo Schneppet titled John von Neumann, Architect der Quantenmechanik and Mathematik. And,
It's fascinating how von Neumann's work, even decades later, continues to have such a profound impact on the development of quantum technology.
Absolutely. For those who might not know who was this guy, the essay mentions that he was a child prodigy.
Oh, yeah.
Fluent in multiple languages.
Right.
And had a photographic memory.
Uh-huh.
Talk about feeling inadequate. But
He was truly exceptional.
Yeah.
What's interesting is that even though his talents clearly lay in mathematics, he initially pursued a degree in chemistry to appease his father, who wanted him to have a more practical career.
Chemistry.
Yeah.
That's a far cry from quantum mechanics.
It is, but even in chemistry he excelled, earning a degree from the Swiss Federal Institute of Technology in Zurich, while simultaneously getting his doctorate in math from the University of Budapest.
Oh.
His dissertation was on axiomatic set theory, which is already pretty mind-blowing for someone in their early 20s.
Okay, set theory. So we're talking about the foundation of mathematics here.
Exactly. And this is where we start to see von Neumann's genius.
Okay.
He wasn't content with just mastering existing knowledge. He wanted to formalize it to create rigorous systems that could explain complex concepts. And this drive led him to make groundbreaking contributions, not just to math, but also to physics, computer science, and of course, quantum mechanics.
Right. And speaking of quantum mechanics, this was a field that was still very much in its infancy when von Neumann entered the picture.
Imagine a time when scientists were just beginning to grapple with the implications of quantum phenomena, things like superposition and entanglement, which defied classical logic.
Yeah, it must have been like trying to assemble a puzzle with pieces from a completely different set.
A great analogy. And amidst this uncertainty, von Neumann saw the need for a solid mathematical framework, a language that could describe this strange new world.
And that's where his book, Mathematische Grundlagen der Quantenmechanik, comes in, right?
Precisely.
Yeah.
Published in 1932, this book was revolutionary. He introduced key concepts that remain central to quantum mechanics today, including Hilbert spaces, which allow us to represent quantum states mathematically.
So instead of trying to picture a quantum system as something concrete,
Yeah.
we can represent it as a point in this abstract mathematical space.
Exactly. And this is crucial because Hilbert spaces allow us to capture the concept of superposition, where a quantum system can exist in multiple states at once. It's like saying a qubit. The quantum version of a bit can be both 0 and 1 simultaneously.
Okay, I think I'm starting to see how this all connects. Von Neumann was basically building the mathematical scaffolding for this entire new field.
He was, and beyond Hilbert spaces, he also introduced the concept of operators, which describe how physical quantities are measured in the quantum world. These operators act on quantum states, allowing us to calculate things like a particle's momentum or energy.
So we're talking about the mathematics of how we actually observe and measure things in the quantum world.
Exactly, and this leads us to one of the biggest mysteries in quantum mechanics, the measurement problem.
Right.
What happens when we try to observe a quantum system that's in this fuzzy state of superposition?
It's like the act of observation forces the quantum world to choose a state.
Right.
Does it suddenly become either 0 or 1?
That's the question that has puzzled physicists for decades. Von Neumann's work led to the idea of the collapse of the wave function, suggesting that measurement somehow forces the quantum system to settle into a single state.
So are we saying that our consciousness, our act of observing, actually affects reality at the quantum level?
That's a question that's still hotly debated. Von Neumann's work didn't necessarily solve the measurement problem, but it provided a powerful mathematical framework for exploring it.
And this framework, these concepts, are still the basis for so much of what we're doing in quantum technology today. It's amazing how it all goes back to this one person's work.
It really is. And we haven't even touched upon his contributions to quantum logic yet, which is another area where von Neumann's thinking was way ahead of its time.
Okay, quantum logic. I have a feeling this is where things are going to get really interesting.
Oh, yeah,
All
definitely.
right, we'll have to pick that up in the next part of our deep dive.
Sounds good.
But for now, thanks for listening, and we'll see you next time.
See you. Welcome back to our deep dive into the legacy of John von Neumann.
Yeah, picking up right where we left off, exploring how his work has shaped quantum technology.
And as we delve deeper, you'll see how von Neumann's contributions extend far beyond just the theoretical foundations.
Last time we talked about his groundbreaking book, mathematische Grundlagen der Quantenmechanik,
Right.
and how it laid the mathematical groundwork for understanding quantum phenomena like superposition and entanglement.
Yeah.
We also explored his introduction of concepts like Hilbert spaces and operators, which are essential for describing and measuring quantum systems.
Yeah.
But how did his work actually influence the development of quantum computers as we know them today? I mean, the essay mentions that the classic von Neumann architecture for classical computers doesn't really apply to quantum computers.
That's true. The hardware and the fundamental principles are quite different, but von Neumann's approach to structured modeling, his emphasis on logical operations, and especially his work on quantum logic, are incredibly relevant.
Quantum logic, could you remind us what that is again?
It's essentially a new kind of logic that accounts for the strangeness of the quantum world.
Right.
In classical logic, things are either true or false.
Right.
But in quantum logic, things can be both true and false at the same time, just like a qubit can be both 0 and 1 simultaneously.
So it's like he created a whole new set of rules for how information is processed in the quantum realm.
Precisely, and this is crucial for designing and programming quantum algorithms, which are the instructions that tell quantum computers what to do.
It's fascinating how von Neumann was thinking about these things decades before the first quantum computers were even built.
He had a remarkable ability to see ahead, to anticipate the challenges and possibilities of fields that were barely emerging in his time.
Okay, so we've got quantum simulation, cryptography, quantum computers. What other areas of quantum technology can we trace back to von Neumann's influence?
Well, one area that's particularly interesting is quantum measurement. Remember the measurement problem we discussed earlier? The mystery of how observing a quantum system forces it to choose a state.
Yeah, it still feels like we're peering into a magic trick every time we talk about it.
It is a mind-boggling concept. But von Neumann's work on this problem, particularly his development of the idea of the collapse of the wave function, has been instrumental in the development of things like quantum sensors.
Quantum sensors? What are those?
They're devices that exploit the extreme sensitivity of quantum systems to make incredibly precise measurements. Think about it. If the act of observation can affect a quantum system, that means we can use quantum systems to detect incredibly subtle changes in their environment.
So we're talking about sensors that can detect minute variations in gravity, magnetic fields, or even time itself.
Exactly. And von Neumann's mathematical framework for understanding quantum measurement is crucial for designing and interpreting the data from these sensors.
It's like he provided the theoretical blueprint for building instruments that can probe the universe at its most fundamental level.
And it doesn't stop there. His work is also relevant to quantum communication, which aims to use quantum phenomena like entanglement to transmit information in a way that's impossible to eavesdrop on. We've already touched upon this with quantum cryptography.
Right.
But it goes even further.
Are we talking about things like quantum teleportation? That always seemed like pure science fiction to me.
It might sound like it, but it's based on real scientific principles. Quantum teleportation involves transferring the quantum state of one particle to another distant particle without physically moving the particle itself.
So not quite beaming people around like in Star Trek,
Haha.
but still pretty amazing. How does von Neumann fit into this?
His work on entanglement and the mathematical language he developed for describing quantum systems are essential for understanding how quantum teleportation works. While he didn't invent it, his contributions laid the theoretical foundation.
So we've got unbreakable codes, super sensitive sensors, teleportation. It's incredible how von Neumann's legacy seems to touch upon almost every aspect of modern quantum technology.
And as Schneppat highlights in his essay, it's not just about the specific technologies themselves. It's about von Neumann's way of thinking, his ability to see connections between seemingly disparate fields, and his commitment to rigorous mathematical modeling.
It's like he gave us a new set of lenses through which to view the universe, lenses that reveal the hidden connections and possibilities of the quantum world.
And these lenses are more powerful than ever as we enter a new era of quantum exploration and innovation.
Well, we've covered a lot of ground, but there's one aspect of von Neumann's legacy that I'm still curious about: the ethical implications of his work. It seems like any technology this powerful has the potential for both good and bad.
That's an excellent point, and one that we'll delve into in the final part of our deep dive. Join us as we explore the philosophical and ethical questions raised by von Neumann's work and consider what his legacy means for the future of humanity.
Welcome back to the final part of our deep dive into the legacy of John von Neumann.
We've explored his groundbreaking contributions to quantum mechanics, his influence on the development of quantum computers, and his impact on fields like quantum simulation, cryptography, measurement, and communication.
But as we wrap up, I'd love to touch on something we briefly mentioned earlier, the ethical considerations surrounding such a powerful field of study. I mean, Schneppet doesn't get too much into it,
Right.
but it's a question worth considering.
Right.
What would von Neumann himself have thought about the potential implications of his work?
That's a fascinating question. Based on what we know about him, I believe von Neumann would have been acutely aware of both the benefits and the risks of quantum technology.
He was involved in the Manhattan Project, after all.
Exactly.
So he clearly grappled with the ethical implications of scientific advancements.
Precisely. And while his essay doesn't delve deeply into ethics, his involvement in such a pivotal moment in history suggests he was deeply concerned with the responsible use of scientific knowledge.
It's interesting, though, that he didn't seem to shy away from pushing the boundaries of what was possible, even when the implications were uncertain.
He was a true pioneer, a visionary who wasn't afraid to explore the unknown. But I believe his drive was always rooted in a desire to understand the universe and to use that understanding for the betterment of humanity.
It's like he was saying, let's unlock the secrets of the quantum world, but let's do it with a sense of responsibility and a commitment to using this knowledge wisely.
Exactly, and that's a message that's more relevant than ever today as quantum technology rapidly advances. We need to ensure that these powerful tools are used ethically and for the benefit of all.
It's a responsibility that falls on all of us scientists, policymakers, and citizens alike. We need to engage in open and honest conversations about the potential implications of quantum technology, both positive and negative.
We need to consider questions of access, privacy, security, and even the potential impact on the job market as quantum computing becomes more powerful.
Yeah, it's a complex landscape, but one that we can't afford to ignore.
Absolutely. And I believe that engaging with these questions thoughtfully and proactively is the best way to honor von Neumann's legacy.
It's about taking the incredible tools he's given us and using them to build a future that benefits all of humanity.
Well said. It's a future filled with possibilities, but also one that requires careful consideration and responsible stewardship.
Well, on that note, I think we've reached the end of our deep dive into the world of John von Neumann. A huge thanks to Jürgo Schneppet for his insightful essay, John von Neumann, Architect der Quantenmechanik und Mathematik, which has been our guide on this incredible journey.
It's been a fascinating exploration of a truly remarkable mind. And to our listeners, thank you for joining us.
We hope you found this deep dive as illuminating and thought-provoking as we did.
Definitely.
Remember, as we venture further into the quantum age, the legacy of John von Neumann will continue to guide us. His contributions have shaped our understanding of the universe and paved the way for technologies that will undoubtedly transform our world. And as we navigate this new frontier, let's do so with the same intellectual curiosity, rigor, and sense of responsibility that characterized von Neumann himself. Until next time, keep exploring.